So, welcome back to another physics lesson, and as ever, I do hope you and your family are keeping well. So, this is a really important lesson, and you can't tackle A-level without knowing about prefixes. So, what we're going to look at is how we write really large numbers in physics, because we're going to be dealing with numbers that are huge a lot of the time. They might be distances to stars or something like that, which we must measure in meters. Yeah, I suppose someone's going to say light years now, aren't they? Okay. But we're also going to be measuring some very small quantities in physics. And because we're stuck with the meter, okay, it's going to be 0.00000, a very small number of meters, something like the width of an atom, the width of a nucleus, or even the width of a proton. So people who are sort of my age and older will remember that their physics probably began all the years ago with a film that kind of started with the very small. It was deep inside the atom, and it zoomed out and zoomed out and zoomed out and zoomed out and zoomed out right the way until it was looking at the whole universe. And basically what it was saying is, physicists, that's our job to look at those things, and we're dealing with the incredibly small up to the absolutely massive. Okay, so we need some way of writing down those numbers with their associated unit. Now, you've got to know these, okay? There are prefixes that go in front of numbers that you're very familiar with. So, we measure distance in physics in meters, nothing else, okay? Or at least keep it simple, nothing else, okay? So when we calculate, we work in meters. But obviously, we're going to talk about distances in kilometers, kilometers. We're going to add the prefix kilo in front of it, okay? And that will make the number we write down smaller. So instead of writing 3,000 meters, we can write down 3 kilometers. Okay, but then we can't put 3 into our calculator unless we know what we're doing. Okay, now there are a whole range of these, and I'll just kind of whiz through them briefly. Tera is a number that's a power of 10 to the 12. It's like 1 and 12 noughts. Massively large number. You probably won't come across that in physics very much. Giga, okay, we talk about gigahertz with microwave signals, and gigahertz, are 10 to the 9 vibrations a second. Okay. Mega, it might be megameters, or it might again be a frequency of electromagnetic signal. So this is 10 to the 6. Okay. Kilo, kilo means that we've taken the number, so like 3,000 meters, and we've divided it by 10 to the 3. To get 3 kilometers. Okay. The centi in here, so centimeters is a sort of 10 to the power 2. It's a bit complicated, centi, okay, because there's 100 centimeters in a meter, and that will confuse you. Okay, I'm going off topic now, but if you do an area and they give you an area in centimeters squared, be really careful. Okay, there's not 100 centimeters squared in a meter squared. There's 100 centimeters that way and 100 that way. So that's 100 by 100. So that's 4 noughts. That's 10,000 centimeters squared in a meter squared. So things you have to deal with at A-level physics. Okay, I've left a dash there to say obviously there's just the regular sort of 1, in other words, 10 to the 0. Okay, then we've got milli, which is for small numbers. Okay, and this can get a bit confusing. Millimeters, thousandths of a meter, so 10 to the minus 3. Micrometers, a micrometer measures very small distances, so that's 10 to the minus 6. Okay. So 1 micrometer will be 1 times 10 to the minus 6 meters. It's a million times smaller. Let's not get into whether it's Italian or what have you. Milli means thousandths of, micro means millionths of, nano, nano, yeah, 9, 10 to the minus 9 of. Okay, and we'll deal with that one a lot in physics. Okay, the nanometer will measure wavelengths of light in hundreds of nanometers. And finally, pico, we don't use a great deal at A level. We do in electronics actually for measuring capacitance, but that's another story. 10 to the minus 12. Okay, now there are other ones, but I'm trying not to do all of them today, just the ones you'll come up with a lot at A level. Now, you need to know these, okay? You need to know them off by heart. So as soon as you see 200 nanometers, you immediately know that in meters, that is 200 times 10 to the minus 9 meters. Okay, I'll give you another example. If you get 0.6 microamps, yeah, you don't put 0.6 into your calculator, you put 0.6 microamps, 0.6 times 10 to the minus 6 amps. Okay, so you can see how this works. It's a clever way of taking what would be small or large numbers and getting rid of lots of sort of powers of 10, as it were. So what we'll do is we'll do a few examples of these, and I'll show you sort of how to add and multiply using these prefix symbols, okay, and powers of 10, and some of the traps you can fall into. Now, I just wanted to point something out about these powers of 10 that go with the prefixes. Okay, you'll notice they always go up in thousands and down in thousands, as it were. Okay, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. That's really useful. And those of you who are taught by me will know I'll go on and on about this quite a lot. I'll compare a way of working with these numbers and set it against standard form. Okay, I actually find, and you'll see in a minute why, using these as the multiplier after a number makes life so much easier. We call it engineering notation, and there is a little button on your calculator called ENG, and it is just so useful. It's kind of a secret function, I always think, that people don't use. I'll very quickly explain what I mean by that. That if you see a number, for example, it says 3 times 10 to the 6 meters, yeah, 3 times 10 to the 6 meters, you immediately know, yeah, it's 3 megameters, yeah. The 10 to the 6 tells you that, okay. If you see 1.2 times 10 to the minus 6 amps, 1.2 times 10 to the minus 6 amps is immediately 1.2 microamps, because you've got that 10 to the minus 6 there. It wouldn't be so easy if they quoted it with a 10 to the minus 5. You'd have to kind of think it through. Okay. There's one other point that I want to make that's obvious, but you will slip up if you don't get this right. Okay. That 10 to the minus 5 is a bigger number than 10 to the minus 6. Okay, so if you've got 10 to the minus 5 amps rather than 10 to the minus 6 amps, obviously if the number in front's the same, okay, so 2 times 10 to the minus 6 amps is lower than 2 times 10 to the minus 5 amps. And people sometimes get that confused in their mind. They kind of get it the wrong way around. Okay, so what we're going to look at now is how we can use prefixes and how they make our life a lot simpler when we're doing calculations. So let's look at prefixes in use now. Okay, and I'll show you some of the traps that you can come up against. It's really easy. Once you've got the hang of it, it's really useful and really easy. So let's measure some current. So let's have a look at current. Okay, and you know that we measure current in a circuit with an ammeter in series. And this is a very sensitive ammeter, and let's say it reads 1.2 microamps. Okay, so written on it is it's a microamp scale and it reads 1.2 microamps. Okay. Now, you can't put 1.2 into your calculator because you're in the kind of right base unit, that's current, but the micro, we don't measure current in microamps in physics, we measure current in amps. So we've got to convert this to amps. And here's the clever bit. Okay, I'm not going to do this cleverly mathematically. I'm just going to say, never mind what that multiplier is, just get rid of the micro. Yeah, just bin it. Okay, and you can type it into your calculator in the way I've shown you. In other words, 1.2, and then micro, if you remember, was times 10 to the minus 6. Okay, and we're now in regular amps. Okay. Now you're going to get a lot of this at A level. Okay, that is, I keep saying this. Okay, that is not how we calculate. We don't calculate currents in microamps. We calculate them in amps. So we've always got to convert to the agreed unit that we use with the agreed multiplier. Okay, but I'll just say again, if you've got micro there, you know in your head what micro means. So just get rid of it. It is shorthand for writing times 10 to the minus 6. Okay, it avoids this sort of nonsense. Okay, 0.000000012 amps. Okay, now I used to do this when I was little. I used to go 1, 2, 3, 4, 5, 6. Okay, and if you do this sort of thing, you're really, you'd be behind the curve, as it were. Okay, because the first thing is 10 to the minus 6. People think, okay, well, 10 to the 6 is something to do with 6 noughts. And they think that 10 to the minus 6 is something to do with 6 noughts. And it isn't. There's 5 zeros there. Okay, so this really is correct, but this really isn't a good way to go. Okay, so don't think about taking a number like that and putting it in a sort of decimal in that way. Okay, just get rid of the micro. Okay, and write 10 to the minus 6. Okay, I'd like to do another example with you just to make another point. So let's do an example. Okay, we've got our little ammeter now, and let's measure a different current. Okay, so we might have to swap scales on the ammeter, and let's say in our circuit we've got a bit more current. Let's say we're measuring 32.6 milliamps. Okay, so that would be a typical sort of A-level number. Now you'll notice that there's 2 numbers before the decimal here, so we'll deal with that in a second. Don't put that into your calculator. Okay, we measure current in amps, and you immediately know that milli is 10 to the minus 3. It's thousandths of an amp. So this is not even yet 1 amp, as it were. Okay, so this is the same as 32.6. Okay, there's the multiplier, 10 to the minus 3 amps. And can you see why that's so useful? We can just get rid of the milli and put 10 to the minus 3 in, and we put 32.6 times 10 to the minus 3 into our calculator. So we're definitely calculating in amps. Okay, so I just want to mention one thing, because 1 or 2 of you might be feeling slightly uncomfortable about this. And I'm not going to have a go at maths teachers who go on and on and on and on about standard form. Look, because this is in milli, we can do this straight away. Okay, this is not in standard form. Okay, it makes life so much easier in this case to not have the number in standard form. Okay, so if I wrote 3.26 times 10 to the minus 2 amps, okay, it's a little bit fiddly in your head to kind of go backwards and go, okay, 3.26 times 10 to the minus 2, how many milliamps is that? Okay, you have to kind of get it out of standard form. Whereas if you write it in this format, in these powers which go up, minus 3, minus 6, etc., okay, you can immediately go that way. So you could say, okay, 32.6 times 10 to the minus 3, 10 to the minus 3 is milli. So I can just write it like that. Do you see what I mean? Okay, so it's a really useful method, this. Now, when you work something out on your calculator, okay, press equals or whatever your calculator does these days, and then find the ENG button, eng. And when you press the eng button, it will automatically put it in powers of 10 to the minus 3, 10 to the minus 6, or what have you. And if you're not happy with the engineering notation you get, I think if you do shift eng, it will shift it up to the power 3, the power 6, the power 9. And doesn't that make that easy? Because your calculator might give that answer, but if you press the eng button, it might give this answer, and as soon as it gives that one, you know that 10 to the minus 3 is milli. Okay, so it's worth giving that a go. Yeah, you have to calculate something first and end up with an answer, I think, and then just press ENG. And after a while, when you get a feel for that, you'll find I've given you a really, really good and useful skill, and you'll keep using it again and again. Okay, so now let's look at where it can get a little bit fiddly. So I'm doing my usual, my students are used to this. Another example. Okay, and what I'm going to say here is you've got a prefix and a unit, and sometimes it's very difficult to see, is it a prefix or is it a unit? Okay, and I think it's worth me saying that basically you will never come across two prefixes in front of a unit. Okay, so you could get some slightly confusing ones if you don't really think it through. I'll give an example. Let's have a look at work done. Okay, so I'll change colour actually. Let's stay with a black. Let's look at work done. Okay, well, you know that that's measured in joules, which is a named derived unit. Okay, but it's also the work done is equal to force times by distance. I won't go into the exact detail, and the force must be, you know, in parallel to the distance you move, all that sort of business. Let's not worry about that. Okay, so it's going to be measured in units of Newton meters. Okay, so you can get some really weird ones like this. Blue pen. So you could get things like 320 of those. Okay. Now, you've got to be careful here because you don't know a unit that is M, big N, little m. Okay. But you do recognise prefixes. You're never going to get a suffix, if you see what I mean. You're never going to get this prefix at that side. So you need to look at that. Probably won't come up at A level, but still, and go, okay, this is 320 prefix Newton meters. Got it. This is 320 milli-Newton meters. Okay, 320 thousandths of a Newton meter, or 0.320 Newton meters. Okay, that's horrible, isn't it? Okay, so spot the prefix there, and what are you going to put into your calculator? You knew I was going to ask this. You're going to put into your calculator 320 milli, there it is, Newton meters. Okay? And it's at this stage you can see why I was saying it is so important that you know what things have capital letters and what have lowercase letters and the order you put them in. Okay? And some of these look really weird, like little m, big N. You know, you can see the confusion here. But once you get your head around it, you can see, that's a prefix. And you know off by heart that milli is 10 to the minus 3. And again, we're not in standard form. We're in engineering notation here, which those of you that know me know I absolutely love. So let's put this to use now. I've drawn myself a sort of cuboid here, and what I want to work out is its volume. Okay, so what's the volume of this object? Okay, well, you might say to me, yeah, FJ, what units do you want the volume in? Well, I'll decide, but today I'd like the volume in meters cubed. Okay, now a meter cubed, you know what a meter ruler looks like, yeah? So a metre cubed is this sort of shape. It's about the biggest box you can carry when it's empty. And those of you who know my classroom, it's about the size that one of the desks takes up. Okay, that's about a metre cubed. It's a flipping big fish tank. Okay, so how many metre cubed is that? Now, if you look at it very quickly, and you hadn't done any A-level lessons, you'd probably think it was quite a massive, great thing because of this large number here. Okay, but because you've done A-level, you realise we've got some prefixes in this system. Okay, there's an interesting prefix, by the way. That's in metres, but it's millimetres. Okay, so sorry GCSE students, I'm a little bit concerned that they might just multiply those numbers together and say it's that many metres cubed, but of course you can see that we have to work in one unit only when we do the maths. Now you can choose what unit to work in, okay, but I would just always convert to the units that we always use. Okay, so don't do anything clever and do it all in millimetres or something like that, because you'll get confused about how many millimetres cubed there are in a metre cubed. There are not 1,000 millimetres cubed in a metre cubed. There's 1,000 by 1,000 by 1,000. Okay, so you have to think that one through. So I would always convert linear lengths to metres first. I know my students will not do this and they'll come unstuck, you know. Sure, if your maths is really good, not a problem, okay? But if you're doing areas of, cross-sectional areas of wires or something, yeah, and you're doing a pi r squared, for heaven's sake, put the r in metres straight away, because you'll struggle with working in millimetres squared, okay? It'll be confusing working millimetres squared when you've got an area. Even worse, working in sort of millimetres diameter and then getting all that confused. But we won't go there. I'm ranting. So what's the area, what's the volume of this one? Okay, so let's do it all in metres. And some of you will notice just how easy that is. Okay, not drawn to scale, I agree. Okay, well, we just multiply the 3 together in metres. So it's 0.06 metres times by, should we do this one? 563,206. Right, how many metres? Micro is times 10 to the minus 6 metres. Hope you knew micro off by heart. Mu, the Greek letter, lowercase mu, comes up a lot. It means lots of things in physics, mu, okay, but in this case it's a prefix, okay. And 250 millimetres, so times by 250 milli times 10 to the minus 3 metres. Okay, so that's in metres, that's in metres, that's in metres. 1, 2, 3 lots of metres multiplied together. I don't know why I left the units out there or even bothered putting them in. Maybe I should put it in just to make the point. You wouldn't normally in the maths. So it's going to come out as 3 numbers times together, metres 3 times, so it's going to come out in metres cubed. Well, I don't know if you bashed that out on your calculator, but I got my super retro calculator here, and this came out as equal to 8.4. I'll leave it there in terms of significant figures and rounding up. I'm not too bothered about that. Times 10, it's come out quite nicely, to the minus 3 metres cubed. Really important you put the right unit on there. Okay. Now, luckily, it's in standard form and it's in engineering notation. Okay. But I just have to do this. My students know I will have to do it. I have to press the ENG button. Okay. And I'll press it again. And I get this number. 8, 4. I haven't done the rounding here. 4, 8 times 10 to the minus 6 metres cubed. Okay. Perhaps I should have left those out. Okay, and just put noughts there. But the point is, by pressing the ENG button, I get the same number, okay? But it tells me straight away that this number here, 8.4 times 10 to the minus 3 metres cubed, which is 8.4 millimetres cubed, is exactly the same as 8.4, I'll put the 4.8 in, times 10 to the minus 6 micrometers cubed. Okay, remember that this one is milli. So it's really handy having things in engineering notation. And if I do, shift eng, and I do shift eng again, okay, it will give me this number in meters. So it'll do 0.00 whatever. Okay, so just making the point there that whenever you do a calculation at A level, look at the units, and for heaven's sake, I would go back to the unit we always use to measure. So in this case, we always use the measurement of length in meters. Then start doing the maths, and I promise you that will help you an awful lot. So I'd like to just quickly do an example where we're adding slightly odd numbers, as it were. Okay, so here's a part of an electrical circuit, and we've got some current flowing into this point here and flowing that way and flowing that way. So we've got 3 ammeter readings, and that current will come out. Okay, later on at A level you'll learn one of Kirchhoff's laws, but the Kirchhoff law you're going to use now is pretty obvious, that if that much comes in, then that much must go out. We can't lose electron flow, as it were. Okay, so we've got to find out what the current is coming out. Yeah, and so we've got to add these, and like I said to you, work in the unit that we always deal with. Work in amps, I would. Okay, you don't have to. Yeah. But it would mean that if you want to work in microamps, then you need to convert this to microamps, okay? And you need to convert that to microamps as well, okay? Which is a bit fiddly. So, working out the total current here, should we do the current total is equal to, so this is this one here, IT, the current total will be 3.6 amps added to 145.2 micro times 10 to the minus 6, yeah, added to 47.8, okay, nano times 10 to the minus 9, okay. So the current total there, all you need to do is add all of those because they're all in amps. And you get good at this and you go, well, 145 microamps is pretty small, okay, it's 0.145 milliamps, so it's a tiny number. 47.8 nanoamps is like really, really tiny, okay. So in fact, the answer is not going to be much bigger than 3.6 amps anyway, okay. But I can be a bit crazy when I set preps, and I could give you 765 million microamps, and then you'd have to think, oh, is that a big lot of amps or a small lot of amps? Okay, so I kind of mess around with the numbers here, or I do 0.0000079 nanoamps, and you think, oh, what's that? Okay, as long as you work in the regular unit, you'll be absolutely fine. Okay, why don't you bash that out on your calculator and see what you get? So if you gave it a go, I hope that's what you got on your calculator. And I'm also hoping that some people watching this are feeling pretty uncomfortable about that answer. Yeah, I know. Okay, 3.6 is a large current compared with only 145 microamps. It wouldn't be if this was a billion microamps. Okay, and 47.8 nanoamps is a really, really, really tiny current. So that current and that current are so tiny that they really add nothing to the 3.6 amps coming in. Okay, so I'm limited by the number of numbers on my calculator screen, but this at A level is rubbish. Okay, and it's rubbish for about 3 reasons, but I'm going to give you 2 to begin with. Okay, it's rubbish because 3.600145048 watt. Okay, don't ever write an answer without units if it has units, if it has dimensions. Okay, obviously efficiency, just write 0.8, yeah, or 80%. Okay, because that's a ratio. But never write a quantity at A level. You will, and it makes me absolutely mad. You know, and I write on people's preps units. Okay, is this 3.6 mega amps? Is it 3.6 microamps? I have no idea until you give me the unit. Absolutely vital. Okay, so that's mistake number 1. Hey, you're never going to make that mistake, are you? Because I've told you. Please don't ever make that mistake. Okay, if you get the units wrong, well, fair enough. you've had a go. The next thing is we've got one decimal place here. We've got kind of two significant figures, and that's the limiting number. That limits. We haven't measured to hundredths, thousandths, tens of thousands. We just haven't measured that precisely. Okay, so all of this lot's rubbish. So in fact, the answer here to one decimal place or the two significant figures is that. Okay, and that shouldn't make you feel uncomfortable, because the other two currents coming in were so tiny that they've made no real difference at all. And maybe at some stage I'll do a video on significant figures, on errors, okay, on precision and things like that. And we'll talk about whether those numbers added meaning or not, okay? Wouldn't it have been, and why it might be weird to write this as 3.60000. That would tell us that this number was being measured to more decimal places more precisely. But I'm kind of going off topic now. Okay, good. So I hope you got that right. So to wrap this up, I'm going to do a really sort of slightly silly example, but A-level again, this sort of thing can catch you out. Okay, so looking at this table of data, I don't know if you can work out what's going on here. I built myself an electrical circuit and I've measured how the current, in amps, I in amps, changes with time. Okay, so as time ticks on, the current was very low, then a bit bigger, bit bigger, bit bigger, bit bigger. Okay, I think some of you immediately are going, God, those awkward numbers, FJ. Yeah, they are. Let's sort that out in a minute. And then the time was over a very long time base. I'm suggesting this is a circuit that should keep its current, and the current was drifting slightly over a long period of time, and it shouldn't drift. Okay, so I've measured the time in, can you see the prefix there? Megaseconds. So that's 1 megasecond, 2 megaseconds, 3 megaseconds. Okay, in other words, times 10 to the 6, millions of. Okay, right, now let's just change this table a little bit and add another column, because I'm finding this current column particularly unhelpful. Okay, so I'm going to add a third column here, which would be more useful. Okay, so at time t equals 0, the current is 0. Okay, I put a slash sign there. Maybe I should put it in brackets. Kind of choice is yours, really. Okay, this, as you can see, is 1,000th of an amp. So what if we measure everything in small m, big A, milliamps? Well, that makes life a bit easier to plot our graph, because this is 1 milliamp, 2 milliamps, 3, 4, 5. Okay. Now, there are lots of traps you can fall into here. How would you plot this data on a graph? Well, I'll draw some axes over here. We'll put time on the x-axis, and we'll put current on the y-axis. Okay, and then we'll put our scale on. Well, it goes from 0 to 5 and 0 to 5. Oh, that's easy then. So we'll just do this sort of thing. We'll go 0, 1, 2, 3, 4, 5. Okay, and we'll go 0, 1, 2, 3, 4, 5. Okay, now the crucial thing here is, sorry to teach you to suck eggs, as it were, you know, if you're going to go 1, 2, 3, 4, 5, that width must be the same as that, which must be the same as that if it's a linear scale graph. Okay, I've seen students do all sorts of weird things in my career. I've even seen them go 1, 1.6, 2.9, 15.2, 73, and I'm thinking, what? Don't put the data on the axis. The axis is the ruler that you're going to put the data onto the main plot of the graph. Okay. Now you'll notice that this graph is a lovely straight line. If we plot the current in milliamps and we plot the time in megaseconds. Okay, so we get a linear graph. Just very quickly come around here and draw that. Probably not going to get it quite in the right place, but that's not the point. Okay, and I could sort of end my teaching there and say, yeah, job done, but it isn't. Okay, because at A level we need to work out areas under lines. Okay, so the area under this line is 5 times 5 halved. Okay, 25 halved in really awkward units if we're not careful. Okay, and the other thing is it's very easy to say the gradient of this line is 1. Doesn't it look like 1? 5 up, 5 across. So the change in y divided by the change in x is the number 1. And it isn't, okay, in the right units. Because this is not in amps and this is not in seconds. Okay, so remember that when you put this number into your calculator, it's 5 times 10 to the minus 3. Okay, and this number here is 5 times 10 to the 6. Okay, so it's not 5 divided by 5, it's 5 times 10 to the minus 3 divided by 5 times 10 to the 6 to give you the gradient. Okay, there's one other way of writing this. You could say the current times 10 to the minus 3 amps. Okay, I like that one. I can see it's immediately in milliamps. 5 times 10 to the minus 3. Oh, I've got it. That is 5 times 10 to the minus 3 amps. And the time, you could say, is times 10 to the 6 seconds. So remember, that tells you what you need to do to that number to get it in the right sort of unit, as it were, in seconds. So this is 5 times 10 to the 6 seconds. Okay. Now, just before I end on this one, this sort of thing is incredibly common at A level. Okay. GCSE, it would just be 1, 2, 3, 4, 5. But at A level, these would be in not the units that we normally use. Okay, look out for it time and time and time and time and time again. Okay, and then look out for it again, because in the rush of an exam, you will put 5 into your calculator and not 5 times 10 to the minus 3. Okay, and they're doing it purposefully to try and catch you out. Now, before you say, well, that's not fair, can you see it is fair? Partly they're testing you, and secondly, isn't it much easier to plot that? Okay, I would be quite interested to know what would happen if I gave that table of data to a GCSE student. Okay, I think a lot of them would really struggle to plot that. They would go, sir, where is 0.001 on my graph paper? Okay, they think it was very low down. Of course, it could just be one box, and 0.002 could be the next box up. Okay, but isn't it so much easier to put it in units of milliamps, but then to remember that you've done that when you do the calculation? So I do hope you found that useful and you've now got a good understanding of prefixes and how they're used, the ways they can catch you out at A level, and how you work with prefixes on your calculator. Anyway, I'm sure I'll be doing some more physics videos before long, and good luck with your physics, and I look forward to seeing you then.